Good morning and welcome to our 2 days webinar, Efficiency in Gear Machining. The technology must fit with the right machining strategy to an energy-efficient gear hobbing process. My name is Heiko Meyer, and together with Jörg Lohmann.
Hello, welcome everybody to today's webinar. Thank you very much for joining.
We will give you an impression about the right machine strategy. As usual, you have the chance to ask directly inside our webinar questions. So feel free to use the chat function or the question function of the webinar tool. Jörg and myself will try to answer most of your questions directly in the session. So please use this opportunity to go directly inside the dialogue with us. So please, Jörg.
Yeah, once again, welcome everybody to our webinar today. The topic is the technology must fit with the right machining strategy to an energy-efficient gear hobbing process. What is the target of this presentation? The target is to give you a deep insight into the design of a gear hobbing process. If we want to realize efficient gear machining processes, we require an energy-efficient surrounding and profound technological know-how. And today, our target is to show you how we actually do this, how we design such a process. And there are a couple of generic questions to answer. One is, which factors have an impact on the efficiency of gear hobbing? And how can we influence those factors and can even make benefit of them? And last but not least, how does a viable way look like in order to design such a process? These are pretty much the questions that we will talk about in the next 45 minutes.
Yeah, there was a small word, energy efficient, but we will see later what is the goal here to be more energy efficient. If we see on a machine tool, what are the main consumer of power on a machine? The drive system of a machine tool have a huge share. That's more than 1,600 watt. If we have the cooling, the compressor, the machine cooling pumps, the hydraulics, of sure the goal is perhaps in the future hydraulic-free machine, but that's not yet ready. And then we have the coolant. And about this, we will talk later because the coolant have a share about 1,200 watt on a machine. So that's of sure also a big driver for an efficient process. What are the measures for energy efficiency on EMAG machines, especially on EMAG Köpfer machines? Of sure, we have optimized cooling units. We use electrical controlled hydraulic power packs. We reduced of the pneumatic consumption, for example, sealing air replacement to electrical drives. We using the standby modes of energy saving. We use energy efficient drives. We have low-loss gear motors, hopeful every time with gears produced on an EMAG machine. And we have auto switch off functions. We're using new LED technology for the lights. But the most important thing is how efficient is the application. And about this, the right selection of the application, Jörg will go in a deep presentation for you.
Yes, okay, thank you, Heiko. So with regard to the process development, we are going to show you this by means of a specific case study. So we have here a project prepared for you. We have a planetary gear. We have a kind of basic project data, such as, for example, the workpiece drawing. On this, we will find the material and its final properties, and of course also its mechanical properties as far as its machining properties is concerned. Then we will find the gear data with the required gear accuracy according to maybe ISO 1328 or the DIN standard 3960 or 62 or any other standard. Then we find indications of the surface finish, roughness values, RA, RZ, or the superficial structure of the gear flanks. And then we have still other basic conditions, such as, for example, the quantity of parts per annum, quantity of parts per batch, the efficiency with which we machine, that means the available machining time, shifts per day efficiency, hours per shift, etc. And with regard to cost per part, the cost structure at the place of manufacture plays also an important role. In the upper right side of this slide, you will see the planetary gear we will talk about. It is module 1.375, number of teeth 31, 15-degree pressure angle, tip diameter 50 millimeter, and it will have a helix angle of minus 20 degree, that means left-hand helix, and the gear length is 20 millimeter. So in order to design this process, first and foremost, we need a clear understanding about the influencing factors on the gear hobbing process, and these are shown in this slide here. On the left side, we have the workpiece. We see the gear data once again, module number of teeth, etc., but also the material specification and its properties. The required gear quality is important too. Then we have the tool, the hob, its macro geometry, that means its diameter, the number of starts, the substrate or cutting material and its coating, and the number of gashes plays also an important role, way more than we know this from, for example, turning. So the hob design plays an important role as far as cycle time and efficiency is concerned. Then there is the process relevant data. The question is whether we go for wet or dry machining. The cutting speed and feed plays an important role as far as cycle time is concerned. And then also the quantity of parts per setup. What does this mean? Well, in case of having flat disc type workpieces, sometimes it's possible to assemble multiple workpieces onto one arbor and gang hob a complete set of parts, or even automatically load a couple of workpieces depending on the blank accuracy and the gear accuracy that we want to achieve at the end of the hobbing process. Then the question is whether we apply a single cut or a multi-cut strategy, particularly in case of having workpieces that might bend while hobbing, or workpieces like shafts that we cannot clamp in a rigid manner. Then it may be necessary to apply a multi-cut strategy in order to achieve the gear accuracy that we need. And at the end, of course, the question of whether we do apply climb or conventional hobbing also has an impact on the final result.
The first question coming from the audience. You show this planetary gear. Where is this planetary gear actually used?
Okay. Well, the workpiece that we have seen now here in this case study, this is a workpiece from an automatic transmission of a passenger car. But, you know, the things that we explain basically are also valid for any other kind of planetary or sun gear, no matter whether we talk about an industrial planetary gearbox or a fractional horsepower gearbox and whatsoever.
Okay, yeah. Thanks a lot.
Sure. Right, okay, so how can we now design the process? We are going to show you now one viable way how to develop an efficient gear hobbing process. This is just one possibility because I think you have already seen that it's a huge variety of different factors, and we need to find the right combination. And in our opinion, we can do this in one way, and this is in 6 steps. And we are now going to do these 6 steps together in this webinar. The first step is the clarification of the quality requirements concerning the gear hobbing process. The definition of wet and dry machining comes next. Then we need to define whether we are going to use a bore type hob or a shank type hob. Then we have to define the hob's material, that means the substrate and its coating. Then we define the macro geometry of the hob diameter, number of starts, number of gashes, etc. And then we are going to define appropriated hob speeds and feeds in function of the previously determined properties of the tool. So with regard to hobbing, we we must consider that we have systematic deviations in this process. What do I mean with systematic deviations? It's the geometric deviations that come from the kinematics of the process. Here in the picture on the left side, we see a hob that engages with the workpiece to be hobbed. And we have here highlighted the superficial structure of a flank. And this consists of the feed rate scallop marks in lead direction and the profile deviation in profile direction. Those two overlay, and this gives us this kind of net, this kind of mesh on the surface. And when it comes to design such a hobbing process, this is not a random product. We decide and determine exactly how this superficial structure should look like. Once again, for better explanation, we see a tooth and we see the feed rate scallop mark. By the way, if you want to understand with which feed rate a workpiece has been cupped, it's simply measuring the length of the feed rate scallop mark, and you will know one by one with which axial feed rate the workpiece has been hobbed before. And here the profile deviations. So the feed scallop mark is made by the hob. The hob has a feed rate in millimeter per workpiece revolution. So after one workpiece revolution, the hob will have passed a certain axial distance, and this is what creates actually the feed scallop mark. And the profile deviations, they come from the fact that we create an involute tooth form with a tool that has straight cutting edges. So how does the kinematics work? We have the gashes on the hob, and we have a basic rack with a straight profile. And the hob tooth come along, enter into the tooth gap following a trochoid shape path. And we have multiple cuts with which we actually create the involute form. And due to the reason that we have an interrupted cut, there we create these profile deviations. So these are the systematic deviations. So step number one, we have to determine what is actually the quality requirement for our gear hobbing process. Here we can see a process chain of a steering pinion, has absolutely nothing to do with our planetary gear, but it's just an example for a potential process chain. So we have turning of the blank, then we have hobbing. We may achieve a gear accuracy class 7 according to DIN. Then we have the hardening process. Hardening causes distortions, of course, no matter whether we go for induction hardening or case hardening. And here in this particular case, we can recover the accuracy by means of a skiving process. That means hard rehobbing on one of our EMAG Köpfer machines. And at the end, we will have recovered and equalized the heat, the distortions caused by the heat treatment. Let's come back to our planetary gear. So here in this slide, we show typical process chains for planetary gears. So we have op 10-20 turning, first and second side. Then we have hobbing. Potentially, there may be the requirement of chamfering. This depends predominantly on the application of the gear later in its gearbox. Then hardening takes place, and afterwards hard turning and grinding of the reference datums is made. For example, hard turning of the shoulders or the hub, the face side of the hub, and grinding of the bore. And then the question is, will there be any subsequent process, or will the gear be used as it is? This depends, of course, on the final accuracy that we need. Here, in our case with the planetary gear, we would have a quality class 8 or 9 without any subsequent hard fine machining process. Or in case of higher requirements as far as accuracy is concerned, or also roughness on the flanks, there may still be an additional generating grinding process of the gear, or even a gear honing process, or maybe even a combination of the two.
Jörg, we see the process chain, and there is important. What I want to add is, offshore EMAG provides you the hobbing solutions, but as well with our vertical pickup machines, we can do the pre-turning, and after the hobbing as well, we can do if necessary, the hard turning and the grinding, and we can do as well the gear grinding with our machines. And what is important, all these technology experts they talking together. Yeah, so it's secured that we have the best total process chain for the production of gears, from starting from the turning to finishing with the gear grinding, for example. That's in addition information from.
Yeah, thank you very much, Heiko. Okay, so let's come back to our case study, Planetary gear. Step number 1, we can check clarification of quality requirements. We determine now that we will have a process that is pre-hobbing before generating grinding, so our accuracy will be class 8 in the hobbing stage. Step number 2, we will have to take a decision whether we go for wet or dry hobbing. There is, of course, advantages, benefits, but also risks, and in order to take a decision, we will have to discuss those, of course. So let's take a look at the potential benefits of dry machining. It's 3 different issues. One is an ecological benefit, a hygienic benefit, and an economic benefit. But let's stick with the ecological benefit first. So there is less environmental pollution possible if we have no production of coolant. No recycling will be necessary. It's, of course, the best what we can do in order to avoid environmental pollution. The second issue is hygienic benefit, less hazards for health of humans. So if there is no coolant, there will be no direct contact with a human skin to the coolant. Some people may have allergic reactions on the coolant. This can be avoided, of course, if we do not use coolant. And there's also no indirect contact. What does that mean? It means simply if we have a machining process and we have coolant involved, there will be oil mist in the air. And of course, we will breathe this air with the oil mist. And actually, this leads to indirect contact as well. And this can also be avoided by dry machining. Then the third and probably most important issue is the economic benefit. There is cost saving for coolant and coolant-related devices. There is shortening the process chain and more economic manufacturing with higher speeds and feeds. Let's dive a little bit deeper into these 3 points. The first economic benefit is cost saving for coolant and coolant-related devices. In the early 90s, people started more and more to introduce dry machining processes in the manufacturing industry. And already at that time, there were 3 gentlemen who have published a book, and they tried to quantify the cost saving that is connected to coolant and coolant-related devices. All in all, a generic statement says that approximately 8 to 16% of manufacturing costs are coolant related and could be saved. And I find it impressive that these 8 to 16% consist of 40% coolant related devices such as oil mist separators, centrifuges for centrifuging workpieces, washing machines, or when it comes to hard fine machining, like in gear grinders, no CO2 extinguishers and no explosion flaps will be necessary. Only then comes the recycling with 22% of saving and then 14% for procurement. This is what these 3 gentlemen stated in the early 90s. Second economic benefit, shortening the process chain. Sounds amazing. What does it mean? With regard to our current process chain, it means simply to avoid washing. If we can avoid washing, of course, it is a cost saving. It not only saves money for the washing operation itself, it also allows us to reduce the so-called workpiece tourism. That means we do not have the handling of the workpieces from one department to the other, to the washing machine, and from the washing machine to the hardening oven, etc. And moreover, of course, if we can avoid this process, we will also shorten the overall time through shop floor, and the workpieces will be available earlier for further assembly.
Jörg, it's a question upcoming. How is cooling achieved if cooling not be done by emulsion or oil?
Well, usually when we do dry hobbing, we use compressed air. So we have blow nozzles that will be installed in the work area, and we use compressed air, a continuous air flow on the process position in order to get rid of the chips and in order to cool the whole system a little bit down. This is what we usually do.
Okay, but then some slides before we learned that the coolant pump needs 1200 watts of the energy or of the power of a machine, and all of us knowing that compressed air is a really expensive good.
Yeah, of course. Compressed air, indeed, you are right, Heiko, is very expensive, that's clear. But we will see that the benefits of dry hobbing, when we have, of course, always under the condition that we have the required quantity of parts to machine, the benefits are way higher in comparison to what we spend on the compressed air. But I'm going to show you this a little bit later on.
Okay, and if I add shortly to this slide something, what is important of sure, if we do dry hobbing, should be the goal as well, that the pre-manufacturing steps or the pre-processing steps should be as well under dry conditions, because then otherwise I need to wash anyway. Yeah, so that's also I think an important point.
Yeah, absolutely, you're right, Heiko. When it comes to the design of a complete manufacturing system in the soft stage, of course, our goal should be to have the complete machining line dry in order to avoid washing afterwards and not to mix this up at all. Because, you know, it's even risky to put a wet workpiece that has been wet turned into a dry hobbing machine, because in dry hobbing we have dry hobbing dust. And this might stick to the workpieces, and then we could even get trouble with clamping workpieces, and this is of course something we need to avoid. Yeah, absolutely right. Good. Okay, so wet or dry machining. Why is dry cutting favorable as far as the removal of chips is concerned? There was a gentleman in 1984 and 1990, later on an additional work from a thermodynamicist called Winkler, and he has explained the effect of easier chip removal by dry hobbing by means of the adiabatic shearing model. What does that mean? We have high cutting speed, and in the shearing zone where the chip is really formed, we have the maximum of mechanical work, and this leads to the maximum friction, and there we will have a red hot zone in the chip's root. And if we have a cutting speed that is high enough, we will reach temperatures that even reduce the mechanical properties of the material being cut in this area, and this is how it works, why the cutting force goes down, and why high cutting speed is favorable concerning chip removal. We have a nice video showing this effect. So on the left side you see this red hot zone in the chip's root. It even bumps a little bit. And this is what favors the chip removing process.
Yeah, if I can ask a question. If I see here red color, I'm getting a little bit nervous, because that's sounds it's a high temperature. And I know from other gear processes for grinding that you have the phenomenon or the problem of a grinding burn. Mm-hmm. Is this also a critical thing here, or how I have to imagine this?
Yeah, thanks. Well, first of all, there's to say, the goal is always to get rid of the heat by means of the chips. So the heat should be removed by means of the chips, and only a small amount of heat, residual heat, will flow into the workpiece and of course also into the hob. Concerning grinding burns, this can only happen in case of having hardened workpieces. But it's indeed a topic when we talk about skiving of gears, like the steering pinion we saw earlier. There this can happen too. This depends on the cutting speed we apply in skiving. It depends on the stock removal, and it depends also on the axial feed rate. These three factors are the dominating factors that put such a process at risk. What can happen if we have too much energy in such a process? It may happen that we have so much heat that we change the microstructure of the previously hardened material again, and then we will have a soft spot on the gear's flanks, and this is what we want to avoid, of course. So there are limits, and we have to know and make ourselves aware that these limits are there, and we know them. Yep.
Thank you for answering this question. And in the meanwhile, also for somebody out of the webinar send a question to us. What are the limits of dry hobbing? Can any gear be dry hobbed?
Well, there are indeed limitations. For example, when we talk about narrow tooth gaps, small pressure angles, and then if we still have on top protuberances, though even smaller pressure angles in the area of the protuberance, then it can become really critical because it's difficult to get rid of the chips. We need to get these chips out of the tooth gap, and there are indeed limitations as far as the profiles are concerned. Yeah.
And you can also stating something, is there a limit according to a module, or doesn't matter the module size of the module?
Well, I think if to give you a ballpark figure, I would say somewhere above module 4 usually people tend to use coolant.
Yeah. Thanks a lot for.
Sure. Well, okay, back to our process design here. We said high cutting speeds is favorable for chip removing. That's nice, sounds good, so let's speed up. No, of course there are limits. Already in the year 1970, people were aware of the fact that the higher we increase speeds and feeds, the more we have effects that favor tool wear, such as, for example, scaling and diffusion. This happens predominantly at high temperatures. So there are limits, of course, and we have to find the economical optimum between the cutting speed and feed and the manufacturing cost. Here in this slide, we see a simplified image of how this can look like. We have speed and feed on the x-axis, on the y-axis manufacturing cost. We have a certain amount of overhead cost, machine-related cost. This is nothing else than cycle time multiplied by the machine hour rate. This goes down, the shorter the cycle time will be and the higher speed and feed will be. But by the other hand, we have tool wear that rises and accordingly the tool cost will rise. If we add up all three curves, then we will have this parabola, the accumulated manufacturing cost, and our job as technology people is simply to find the minimum of the manufacturing cost when it comes to designing such a process. So the potential of dry hobbing has also been shown in the year 2000 by a gentleman called Sulzer. He was, to the best of my knowledge, the first to publish the potential of dry hobbing by means of these charts. We can see two charts. We have on the x-axis the tensile strength of the material to be cut, and we have on the vertical axis here the cutting speed, and here in the second chart the maximum chip thickness. This is more or less proportional to the axial feed rate of hobbing. And we can see different kind of substrates and the difference between wet and dry. So we have PMHSS dry and PMHSS wet, and the same here for tungsten carbide. And we can see that already at that time in the year 2000, there was the statement that we can increase cutting speed to approximately 30% when it comes to dry machining. And we also see an important difference between tungsten carbide and PMHSS here. Tungsten carbide allows lower maximum chip thicknesses, for example 0.16 in comparison to PMHSS.
Jörg, if we look shortly to this diagram, what I'm wondering is here we have a maximum chip thickness, and then for dry we have also a minimum, but I don't see something for wet cutting. Can you explain this topic a little bit?
I mentioned earlier that when it comes to dry hobbing, our goal is to get rid of the heat by means of the chips. And the chip, if the chip should assume the heat, it needs a certain volume, otherwise it cannot assume the heat. And this is why at that time people have determined a minimum chip thickness for dry hobbing, because otherwise we get thermodynamic problems because the heat will stay either into the workpiece or the hob. Yeah. Okay?
Good, thank you for this additional.
Sure. There are, of course, also risks when it comes to dry hobbing, and the risk is the superficial defects that we find in dry hobbing, but we will not find this in wet hobbing at all. The superficial defects have been defined as all geometrical deviations that are of non-systematic character. We see them here in these three pictures. First and foremost, there's the scratches on the flanks. This is just an optical effect. But then there is the material greasing and the chip welding. And material greasing means that really the steel will be greased along the lead of the flank, and we will have locally an increased stock allowance that we do not want. And let's imagine what may happen. You have the carburizing process. You will have a bump on your gear tooth. You will carburize this. It will be hardened. Afterwards, there may be a grinding process. You grind the stock allowance off, and then you might have a lack of hardness in one spot, and this is what we do not want. Then the next is the chip welding. In case a chip sticks to the hob, it can come back to the process. It will be red hot, and it might weld itself really into the tooth gap. And imagine what happens to a honing ring once this workpiece is loaded to a honing machine. It will, of course, damage this honing ring immediately, and this can really cause trouble in the process chain. So for successful application of dry hobbing, there are a couple of basic conditions necessary. First of all, what we told earlier, it's risky to bring a wet part to a dry hobbing machine. The workpiece volume, let's assume we have a small tiny pinion. We remove more than 50% of the body of the workpiece by the hobbing process. So where should the residual heat go? These workpieces will, of course, become quite warm after having been cut. Then the third is the quantity of parts. Do we have the required quantity of workpieces in our project that allows us to do long-term process analysis? That means, may we apply different cutting speeds and feeds, monitor the tool life? This is something that we should be able to do in order to have an efficient dry hobbing process. And then, moreover, we should be ready to use workpiece dedicated hobs. Well, in our case, we have seen there are benefits when we do dry hobbing. Our example here is related to a project with high quantity of workpieces per year. So we decide we want to go for dry machining in our case and make benefit of the advantages we have heard about. Next step will be the definition of shank type hob or bore type hob. We will have to discuss these both. In the picture on the right side, you will see a hob in bore type execution, and underneath you will see a hob in shank type execution. The bore type hob has usually a kind of keyway in order to transmit the torque. Here we have a longitudinal keyway according to DIN 138, and there are advantages and disadvantages of both. Advantage of a shank type hob is that there are less interfaces between the drive and the tool, so higher accuracy is possible. Well, bore type hobs need to be assembled to a hob arbor assembly, of course, and this usually means more interfaces and might lead to a loss in precision. The biggest advantage of the shank type hob is that we can have longer shifting length. This comes from the manufacturing process of the hobs. A bore type hob has a very precise bore and tiny tolerances with regard to the external gear. And the honing of this bore cannot done until eternity as far as the length is concerned. So the bore type hobs are usually limited in their length. And this is not the case with shank type hob since they are machined between centers. And that's an advantage, so we can make shank type hobs simply longer. A disadvantage for the shank type hob is that it is way more pricey. They are expensive, and also when it comes to resharpening, there is more resharpening work involved, and the maintenance is simply more expensive. And on top comes the fact that a shank type hob is usually machine dedicated because it has a machine dedicated interface. In case you have a Köpfer make 160, for example, and we have a designed shank type hob for this machine, it will be difficult to exchange this with any other machine.
Jörg, if I may, can ask here a question.
Sure.
What's going to, we saw the two different type of hobs. Is there also, you told it's a difference in price and so on, but is this also a difference in the availability? Is there more manufacturers of this type of hob, or how is the delivery time?
Yeah.
Can you give us there some more information?
Well, with regard to the delivery time, usually the tool makers, they have hobs in bore type execution on stock. That means they have the blanks on stock, and once they receive the order, they start to profile grind these hobs. That means they have, no matter whether it's tungsten carbide or PM HSS or MC90 or Speedcore, they have the blanks in their stock, and then they have the possibility to start from there. This is not the case with the shank type hobs, because shank type hobs still, the blank still needs to be sintered. This is the reason why usually bore type hobs are available with make some 6 weeks maybe, and shank type hobs usually have a delivery lead time of around about 12 weeks. There's a huge difference between the two. Yeah. Right. Why is the hob length so important? Let's take a look at the hob shifting. What means hob shifting? Here in the right side of the picture, we see the workpiece being hobbed. Here we see the hob, and hob shifting means simply that after each workpiece having cut, we make a shifting step and move the hob along its longitudinal axis. And why do we do this? Well, simply in order to distribute the tool wear as uniform as possible over the usable hob length. Usable hob length, here we see the usable hob length of a hob by means of this blue arrow, and effectively usable is only the green portion of it. This is because we have the profile pre-cutting zone. This area is used simply for removing material out of the tooth gaps. It's a kind of just roughing. Then we have the profile generating zone, LP0. Here we have LP0.5 on this side and also 1 time on this side. And this is the area where really the profile of accuracy relevant cuts happen. This is where we make the quality. And we have to deduct those from the usable hob length, and you see that there's only a portion that remains, and the longer the hob, the longer this portion will be, of course. That's why it's important to have possibly a long hob. What does this mean cost-wise? To come back to our Planetary gear, here is a cost analysis for tool costs. We compare the shank type hob with the bore type hob, both hobs of diameter 50, usable length 180 versus 85 millimeter. Shifting range is also shorter, of course. Price-wise, we have €2,500 for the shank type hob against 1,500 bore type hob. So, as I mentioned already, the shank type hob is way more expensive. Also, the maintenance, the resharpening is way more expensive. Both hobs can be resharpened 15 times, and parts per resharpening differs considerably due to the different shifting length. We can machine 6,500 workpieces with the shank type hob and 2,500 with a bore type hob. And if we now add up the whole cost, that means purchasing plus also the hob maintenance, and we divide this with the total number of workpieces we may machine with such a hob, the result is considerable. We have a reduction on the tool cost per part of 50% in our case here. So it's 6 cents with the shank type hob and 11 cents with the bore type hob. So when it comes to take a decision, of course, we will go for the shank type hob in our project here. So let's come to the next steps. We will have to define the hob substrate and its coating, the definition of the macro geometry of the hob, and we will define the cutting data, that means hob speed and feed. But now it will be difficult to take decisions because there are different variants, and we will make a determination of these parameters by calculation of different variants at the end once we have run through the discussion of each individual point. Here is an overview that you maybe know from the one or the other school book. It shows us on the x-axis the toughness that is proportional to the feed rate. It shows the wear resistance and the cutting speed, and it shows us different kind of cutting materials or substrates. On the right upper side would be the ideal substrate, and we see what happens. We have HSS with coating. It has a big advantage. You can run it at a high cut feed rate. In comparison to this, you have the tungsten carbide hob, and you can run this with a high cutting speed. So these are the advantages of both cutting materials. Moreover, there's to say that tungsten carbide, due to its hardness, is relatively delicate as far as the handling is concerned.
Jörg, if I can also here, if we look to this table or to this diagram, we see here ceramics.
Yeah.
Is this, for example, a turning, ceramics could be a solution for special operations. How is it with hobbing with a ceramic tool?
That's a good question. Why aren't hobs made of ceramics? Well, Köpfer already more than 20 years ago has really started to make trials with ceramic hobs, and they have run those hobs with incredible cutting speeds. It was really amazing. But the problem is that how would you like to resharpen a hob that is made of ceramics? There is no possibility to resharpen them, and that was the reason why, the project ended there. And this is why we have these three cutting materials available today. Okay?
Okay, thank you. Yeah.
Once again, these two slides from Sulzer, it shows you simply the possibilities that both cutting materials offers. We see exactly the same we saw before. It fits. The PM-HSS is better for the higher feed rate, but for the lower cutting speed. Okay, next step, we have to determine the hob properties. In order to determine the macro geometry, we need to understand how a hob is made. We see it here in the picture on the right side. A hob is actually nothing else. It's basically just a worm, and this worm has gashes. And this is where the cutting teeth come from. Then it is ground, it is profile ground, and this is how the clearance angle of that usually is about 12 to 15 degrees is made. There is a rule that says the helix angle should not overstep 6 degrees in case of having straight gashes. Why is this the case? Simply because otherwise we would get deviations in the profile, and in order to avoid those, we should accept not to overstep the 6 degrees. Well, one might overstep this. For example, when we talk about worm gear hobbing is a different issue. There we may have spiral gashes, and this is because the diameter of the hob is given by the worm that engages later with the worm gear. This is a different case. The straight gashes help us also with regard to the cost, because it's way easier to resharpen a hob with straight gashes in comparison to one with spiral gashes. From this rule, there come a couple of other statements. The bigger the module, the bigger the hob will be, of course. The higher the number of starts, the higher the OD will be. That's also clear if we want to keep the 6 degree constant. The bigger the OD, the higher the number of gashes can be. We have a bigger circumference and we can have more cutting edges on the circumference. And then last but not least, also the accuracy of the hob plays an important role. Nowadays we even have precision degrees up to 4A quality for hobs.
Jörg, before you stated that we look to a pre-hobbing process in DIN quality 8.
Yeah.
Which hob you suggest for this, or which hob accuracy you suggest for this process?
Yeah. Well, since it's a roughing operation, I would say A is enough. In order to be on the safe side, honestly, I would purchase a hob of 2A quality. Then we are sure that we will not get trouble, because it's a little bit like printing a book. If you have a pitch deviation in your hob, you will find this also later in your gear, also concerning the profile deviations. Which impact has the number of starts? Here we see a simulation of the tooth flank of our Planetary gear. This is the root, this is the tip. Here we have a hob with 1 start, feed rate 2.2 millimeter per workpiece revolution. Here we have a hob with 4 starts, and what happens? It's not the feed scallop marks. This is constant, in both cases round about 8 microns, but the difference is predominantly in the profile. This comes because the number of starts is here in this equation. We see this in this fraction, it comes square. That means if we increase the number of starts 2 times, we will have 4 times higher deviations. And we will see this also in an inspection chart of the gear. In this case, when it comes to the number of starts, here with the profile-related parameters, the individual profile deviation FF alpha and the accumulated pitch deviation big F alpha. And here in the lead, we will also see the feed scallop marks. These correspond then to the parameter FF beta and will also have an impact on the accumulated lead deviation
Jörg,
F alpha.
I
F
got
beta,
information
sorry.
that we have to hurry up a little bit. Anyhow,
sure.
I will ask you here something. If we look here to the single pitch error and the sum pitch error as well, and then the run out, it looks like a little bit, not strange, but a little bit special. Can you explain why it looks like it looks like?
Very simple. This is the pitch deviation in the gear, and you can see positive and negative values. It's like a pattern, and this comes simply because this workpiece has been hopped with a 2-start hop, and what we see here is the deviation from the hop one by one in the deviation of the pitch. Okay, so now we come to the last point here. We have to determine the cutting speed and feed. The feed, as already mentioned, influences the feed rate. We will find this later in our chart. So there is a quality-wise, there is a limitation of the feed rate. And the second parameter that limits the feed rate is we have to avoid excessive tool wear. Here on the right picture, we can see a hop tooth and we see a kind of crater wear that we usually have in gear hobbing. And we, of course, want to apply our hops in a meaningful way. The feed rate has also an impact on the superficial structure of the gear flanks. Here we see the corresponding equation. We see in the numerator the axial feed rate FA. It also comes square. That means if we triple the feed rate, we will have 9 times higher deviations. Here is the lead, root diameter, tip diameter. Here we have with feed rate 2.28 microns, and with 6.7 we have 76 microns deviation. So we may not, this is not usable anymore actually. So with regard to limiting the feed rate in order to avoid excessive tool wear, there's a possibility that has been developed by Bernd Hofmeister. He has written his thesis at University in Aachen, and he has developed this empiric equation that we see here, and we can calculate the maximum chip thickness depending on the process and gear and hop data. And in hobbing, we have single flank chips, double flank chips, and triple flank chips. And here, in order to get a picture, we can see what we calculate. We calculate actually the cross section, the thickness of such a 3-flank chip. And this is an indicator, to come back to our diagram from earlier, that shows us whether we stress our tools too much or whether we are still okay.
Jörg, if I look here to the diagram, I see 320 meter per minute cutting speed.
Yeah.
If I keep in mind that I saw applications running, dry hobbing applications where we have more than 700 meter per minute cutting speed.
Yeah.
Can you explain a little bit why is there the difference, or what is really the reality?
Yeah, look, Heiko, of course, you have to consider that these values are nearly 25 years old. Nowadays, we have a huge database. EMAG Köpfer has a lot of know-how. We know exactly how to run our hops. And so it's not seldom that we really run in a soft finishing process with a 2-cut strategy close to 1,000 meter per minute in the second cut. This is absolutely true. So these values are quite moderate, quite modest. All right, okay. So now we come to the end. So now we do the definition of these parameters by means of calculation of variance. This is a big table we see, and we see that we have made a variation of the hop dimensions. We have hop diameter that starts from hop diameter 32, single start 12 gashes, and we go up to diameter 80 millimeter, 5 start 21 gashes. And now we calculate the cost per part over the machine hour rate and also the tool cost per part for each individual substrate. Here for PMHSS, here speed core or MC90, and here tungsten carbide. And we take a look at the total cost of the process, and there is one process that is a little bit outstanding. This is here the process with the tungsten carbide cutter, 21 cent, consisting of 6 cents for tool cost and 15 cents for machine cost. And this is this hop macro geometry. It's diameter 50, 2 starts, and 15 gashes. So obviously this is the most efficient one for machining our planetary gear. Here's the cycle time calculation based on a Curb 460. For sure, one of the fastest gear hobbing machines you will find in the market. Cycle time is less than 9 seconds. On the upper right side, you see the water-cooled direct-driven hob head with HSK high-precision interface and a shank-type hob. And this is how this process looks then in reality. This is the Curb 460, a slant bed design machine. It is equipped with automation. It has a gantry loader. Here we see the chute magazine where the workpieces roll down by gravity on multiple rows. And there is the so-called servo distributor that presents the workpieces to the gantry loader. The gantry loader is a high-speed loader with double rotary gripper. And here we see how the workpieces are exchanged in the work area. This is the hob that we have determined earlier together. It's a shank-type hob, diameter 50, 15 gashes, 2 starts. And we can also see this little auxiliary tool coming from downwards. This is in order to remove the burr on the face side of the gear.
Jörg, thank you very much. Again, it was really interesting. I hope you get a good impression how we have to design the gear process. Shortly we saw already a K160, but in the end we will talk shortly about the machines. So we have here the K160. That's the most popular EMAG Köpfer machine where we are able to do gear and shafts up to module 2.5 millimeters. You saw the really fast loading and unloading so that we can really create fast cycle times. And one more interesting machine from EMAG Köpfer is the HLC 150H. That's a machine capable up to module 3.5. And what is important here, that's a universal solution. You can do hobbing. Offshore you can also skive hobbing. You can do warm milling in single catch strategy. And what is important, since some weeks we are able to do also power skiving on this machine without any modification of the kinematics or the mechanical components in the machine. So that's a really additional point, that you have a really flexible machine. You can do as well power skiving. And how we can do this? We have a huge milling head swivel angle, about -45 to +135 degrees. And we have a powerful milling head with a power of 28 kilowatts. So this gives you really good opportunities. And what is important, if you have a project where you need urgently a machine, EMAG Köpfer have every time 1 or 2 machines of each type available for quick delivery. There we have then only to look how is the delivery time of a hob head and the clamping fixture, and then you can get such EMAG Köpfer machine within 3 to 4 months after your PO. This could be also interesting solution for you. If the modules getting bigger, the dimension getting bigger, we have to jump to our EMAG SU products. That's then vertical machines, vertical hobbing machines, CLC 200, CLC 300. There we are capable to do modules up to 8. And I have no slide for this at the moment here in this presentation, but what is important as well, we can also provide you machines for the hard fine finishing operation with thread wheel grinding machines, G160, G250, G400, where we can do thread wheel grinding and as well profile grinding. And we have different other machines in our portfolio for doing rotor shaft milling and as well rotor grinding. So many interesting products in our portfolio for gear production. If you have not more, there is one more question upcoming, Jörg. Is dry hobbing a valuable option for small quantities as well?
Okay. Well, if you remember earlier, I explained that we should have the required quantity in order to make trials. We really should have the quantity to make analysis concerning the tool life. And this is one important thing. We need the possibility to optimize this. And you know, many of our customers are also job shoppers, small shops where they make many different kind of gears. Usually a hob with a basic rack, a standard basic rack, can be used for different kind of number of teeth. But when it comes to dry hobbing, we should really determine the hob precisely for one individual gear. And this may lead to the effect that you have a multi-start hob that you should not use for a small number of starts, etc. So honestly, you know, wet machining is still the more forgiving process. So for small quantities, I would recommend rather to use coolant.
Okay, thank you very much for
You're
this
welcome.
final explanation. There I have only the opportunity to invite you to the AMB exhibition, which take place from 10th to the 14th of September 2024 in Stuttgart. There you can meet Jörg, you can meet the whole EMAG team, and you can see as well a HLC 150H, you can see a CLC 200 machine, and you can see several other applications from our side. So we look forward to welcome you on the show, and thank you very much again, Jörg.
Thank you very much for attending. It was really amazing, and we are pretty much looking forward to meeting you personally on our booth.
And as well, thank you very much for your time. We look forward to welcome you on one of our next webinars. Check out the dates on our webpage. Thank you very much. Have a good day.
Thanks. Bye.